All right, hello and welcome. My name is Alexander. I work for Grammarly, and today I'm gonna talk about virtual machine for regular expressions, which can seem like two very distant and non-connected topics, but after this talk, you'll see what is common between them. We'll start a little bit with theory. Raise your hand if you know what is a regular expression. Okay, so pretty much all of you, that's very good. So we thank this guy, Cole Kleene, for the invention of regular expressions. He was the person who sometime in 50s formalized the concept of regular languages, and then he was involved in the creation of a syntax which evolved over time, and this syntax was to define how to check and how to parse these regular languages. And basically, regular expression is the text matching automaton. This is an example. Here it is, how regular expression works. If you're familiar with the syntax, you'll know that this regular expression will match any string that starts with one or more occurrences of A, followed by an optional B, and then you have alternation between C and then 0 more occurrences of D, or just E, and that should be the end of the string. In such a way, the first string will match this regular expression, or you say that regular expression matches this string, and the second string will not. Because, why? Because there is no C and no E, so yeah, it will fail at some point, right? The other way to represent regular expression is the finite state machine. This is, yeah, the same regular expression over here, and we say that we start at this node, the starting node, and we can get to the node number 1 if the current symbol is A, and from there we can loop in this cycle of A, staying in this first node, and from there we can get by B into the node 2. That's our optional B. Or we can immediately go by C to number 3, and there is this D loop here, or we can get to node number 4 by E, and from there, if that's the end of string or end of sequence, we can get to the end of the automaton, the state machine, which means a successful match. And this is a little bit simplified version, because there is actually also an explicit fail state in which you can get if you cannot go by like any legal transition, you have to go to this fail state, and that means that the regular expression is not matched. So at this point you might ask, why should we care about this? Why would you want to implement regular expressions yourself? And that's a valid question, because pretty much every modern programming language has a regular expression engine built in or available as a library at least, right? That's true, but there is one drawback to pretty much all of them, that those regular expression engines, they support only those are character level regular expressions. So you can only match strings with them. You cannot match, for example, arbitrary objects. And at Grammarly, one of parts of our system, we define these quite complex rules for checking grammar and semantics and other things in the language. And those rules, they don't operate on the character level, they operate most often on the token level, where the token is words and punctuation, basically. So first we split the text into words, into these tokens, and then we want to define the rules on that sequence of tokens. In this example, and it doesn't make much sense, but just serves as an example, we can say that the person is alternatively an optional honorific, that is Mr. or Mrs. or something else, and then one or more occurrences of a token that is present in the first name dictionary, so like any first name, and in the end there should be a word that exists in the last name dictionary. Or alternatively, it could be an optional determiner and something from the dictionary of professions. So this is an example of some part of a rule that we might use in our work. And so you see that this rule, it maps very, it looks like a regular expression because it is a regular expression in the end. So what are the ways to implement regular expressions? The first common approach, which is most often used in different programming languages, called backtracking, and its main characteristic is that it has potentially exponential runtime, which means like exponential from the length of input. And as programmers, we know that exponential complexity is probably not very good, but we'll get back to that. First, I want to show you a very simple backtracking regexp implementation. It was written by Rob Pike some times ago. Rob Pike is a software engineer who created a Go language. He works at Google now. And this is very, very simple implementation written in C language. You have a match function which takes two strings. Basically, it's a regular expression string and the string we match on. And then we check if that's the end of regular expression, we return 1, which means success. The regular expression ended. And if the second character is star, means this Kleene star, which means 0 or more occurrences, we call this match star function. I'll mention it later. And then if it's not the end of text yet, and either the current symbol in the regular expression is a dot, which means any symbol, or if the symbol in the character in regular expression and the character in the text match, then we recursively call match on shifting one character from the regex and one character from the text. And this match starting basically recursively calls match while the character under the Kleene star matches. So yeah, it's a very concise implementation. It's just 15 lines of code, and in the time when you can barely fit like 2 setters in this amount of code, it's very concise, very short and simple. The bad part, like I've said, is this thing has potentially exponential complexity. If the regular expression is quite complicated, you can get this exponential explosion, and your regular expression will never finish. So this is a recipe how to kill a snake. You start a Python interpreter, you import the regular expression library module, and then we have this string of just 50 A letters in a row. And if you call rematch with this regular expression, quite innocuous, it's like just A or double A, and there is a Kleene star and B. If you call this function, it will finish approximately in 5 or 6 years. So by the time it finishes, user will probably not care that it didn't match. And that's the backtracking implementation for you. Actually, in Java, it's the same. You can try it in Java with the standard pattern implementation, regular expression implementation, and it will have the same behavior. So yeah, it doesn't work for us because in Grammarly we have around 10 million daily active users, and they are all writing texts that we want to check to improve their writing. And yeah, it's very large amount of texts, and if you have a lot of complicated and big regular expression, there is high probability that because of some bug you'll get this exponential explosion somewhere, and your program just hang. So we didn't go with this implementation. There is a second approach called full finite state machine unroll. And this is kind of like the full state machine that I showed on previous slides. You take this regular expression, you unroll it completely into the state machine. The benefit is that the runtime becomes linear. You certainly know how many steps you'll be able to take. But the bad part is that you just shift this exponentiality from the runtime to compile time. So the compile time becomes exponential, and also your regular expression will possibly need exponential memory just to unroll this whole state machine. So I don't know if anyone uses this approach nowadays, just for theory. We didn't go with that either. And there is this third approach called dynamic finite state machine unroll. yeah, it's like you construct this deterministic finite automaton, but you do that lazily. So on each step, you construct just the necessary parts. You don't unroll it completely. And this keeps the runtime nice and linear. It just depends now on the length of the sequence and the length of the regular expression. But it's still linear, so why not? There are a few known implementations of this approach. One is Google Re2 library, which was originally written for C++. And there is a port for Java. And yeah, they guarantee the linear runtime. They don't support some of the features of regular expressions like back references or not backtracking. Yeah, just negative look behinds, those kind of things. But yeah, they guarantee the linear runtime. Then there is this regexp library for Rust. They say that's the fastest regular expression implementation in the world. It's partly true, but yeah, they use the same approach. And the third approach, which I will finally talk about today, is the approach of creating this virtual machine that will kind of match your regular expressions. It's from quite an old paper I found on the internet, and it's a very interesting one. So just a few words about virtual machines, if by chance you don't know how they work exactly and what the concept is. But before we talk about virtual machines, I'll just show you very primitive example of a real machine. So let's say this is an x86 machine, and we have some machine code. Here it's actually assembly, but let's pretend it's machine code. And there's this nice CPU over here. It will execute this machine code in order to do something. And there is a set of registers here, and one of the registers is special. It's called instruction pointer that will point to the current instructions the CPU will execute next. Yeah, and some of the instructions, they can actually change this instruction pointer. So this is how jumps and conditional jumps are implemented. So whatever you write in high-level languages will eventually compile into this in some sort. Let's make it a little bit more complicated. So we have like multi-process operating systems right now and multi-core CPUs. So there is not just one thread, there are multiple threads running on any physical machine. And each of those threads, they have their own register bank where they save some immediate data, and also their own instruction pointers. So you can imagine this program, there can be multiple threads running different parts of this program at the same time. So that was a physical machine. How does the virtual machine looks like? Well, it's kind of similar. But instead, so you still have a CPU, but instead of executing this code and tracking these registers on the hardware level, it does that on the software level, so it's kind of emulation. This CPU, it knows that it has some code that it needs to execute, and it knows about the threads, and it chooses which thread to execute first. So yeah, it's emulation of sorts. And there are multiple types of virtual machines you may be aware of. The first one, very common, like VirtualBox or VMware, where the virtual machine and like the host machine, virtual machine are similar. They execute the same. The virtual machine has the same code that needs to be executed. It's just the level of emulation that is added, but it's still the same native code. And Java Virtual Machine is different because it has its own bytecode. It's no longer the same instructions as on the host platform. It has its own bytecode, and we use Java Virtual Machine to abstract away the details of each architecture so that we can write programs that will run on every architecture regardless. And the third one, again, which I'm gonna talk about, some domain-specific virtual machines that you can just invent how many you like if you have a problem that fits this approach very well. So that's what we did. We created a thing we called token regex virtual machine, or TrexVM. And here it's a short specification of it. This virtual machine, it consumes the input sequence one token by token, and it never goes back to the previous tokens, which is the way to guarantee the linear runtime. Then the instruction pointer, like in the physical machine, it tracks the current instruction to be executed. And then there are 3 instructions. So this virtual machine needs only 3 instructions. Does anyone know how many bytecodes the JVM has? Please? Yeah, that's correct. So it's around 200, 202, I think. At least that's what Wikipedia writes. But yeah, so JVM has 200 bytecodes, so we can do it with just 3. And those bytecodes, the first one is compare. So you say compare and some predicate, or let's say some checker that will tell whether the current token matches or not. And if it does match, the instruction pointer is incremented, so we do the next instruction. If it does not match, this thread dies. There is the jump, the jump instruction, which takes a label, and this instruction modifies the instruction pointer so that the instruction under that label will be executed next. And there is third fork instruction, which creates 2 threads from 1 thread. So what I haven't told yet is that this virtual machine is multi-threaded. There are multiple threads running in parallel. And what fork does, whenever the thread does the fork instruction, 2 threads will spawn, 1 thread will continue from the next instruction, and the other one will jump to label. Just a few more details. All threads are executed in lockstep. So we only execute compare instructions when all the threads point at compare. So whenever the thread does not point on compare, we try to unroll it further. And and execution continues until either all of the threads are dead, which means regular expression failed, or at least 1 thread succeeds, which means it's matched. This is a short demonstration. This is a sample run of this T-Rex virtual machine. We have the program on the left, just 3 instructions here, and this is our input string. It's the string that we want to match. And we have 1 thread. It points at first instruction. Instruction says compare A. So we check whether the current pointer in the input sequence points at A, and it does. So the thread propagates next. We see that the input pointer shifted and the instruction pointer shifted as well. Now we have fork L1, which means 1 thread will go to the next instruction and the other one will jump back to L1. Okay, let's do that. We have 2 threads now. They both point at compare, which means we can execute this compare instruction here, but the current character is A, so only this thread, the second thread, will survive, and this one will die. We do that. We have fork again, so we fork again A in the input string. Thread number 3 survives. Thread number 2 dies. We do that. Fork again. Oops, sorry. And almost the same, but now B is the current character. So thread number 4 dies, and thread number 3 goes next. It reached the end of the regular expression, which means success. Can anyone guess what sort of regular expression did we just run? No, it's actually very simple regular expression. A plus B, yes, not A star B, because there is 1 obligatory match here, right? So that's true, that was A plus B, very good. Some more guessing, a little quiz for you. What does this regular expression do? Let's divide it in parts. So these first 2 instructions, there is a fork that jumps over A, and another thread will try to match A. So what, sorry? A question mark, right. So this part is A question mark. Then we have fork L2 all over here, and the other thread will try to compare B and then jump back to L1. So this is B star, right, because it can jump over this part completely, 0 matches, or it can just spin in a loop. And the final one is just C, That's right. Okay, so now we have a concept of a like prototype or virtual machine. It can really match regular expressions, very good. But so far we can only just say whether the text matches a regular expression or not. What we want more is at least the match groups, so we can actually extract something from the text we are matching with regular expression, right? So we added the support for the match groups. For that we had to redesign the virtual machine a little bit. Now each thread has its own register bank, like on the native machines. So not just the instruction pointer, but other registers where it can save some information. And we have a few new instructions. 2 instructions, save left and save right, are very simple. We, whenever the thread reaches the, say, save left instruction, it saves the current input pointer to its register bank. So it's, remember, this is the beginning of some group. And save right is the opposite one, just to save the end of a matching group. And then 2 new instructions, we had to replace the fork instruction with 2 forks, fork jump and fork stay. The thing is, we introduced the concept of priorities here, thread priorities. And in order to support priorities, we now have 2 fork operations. The difference between them, is that the fork stay will give higher priority to the thread that goes to the next instruction, and the fork jump will give higher priority to the thread that jumps to the label. And we changed the ending condition, so we now execute the regular or the virtual machine until all threads die or the thread with the highest priority ends. Okay, so I need a volunteer here, a person who would come here and just work as an interpreter of this program of our virtual machine. Please, it won't be hard. I will help. Thank you, Lucas. What do you need? Yeah, so you can. Here's a pointer. Press this. It's a laser pointer. Up. Just you're too quick. Let's just start with this. Yeah. Again, on the left, the program, the input string, and on the right, we have the thread registers now. They are empty so far. And the first thread, we only have 1 thread, and it points to the save left. So what happens if we go to the next slide? Like, what will happen now? The position, yeah, the position in the input string, that's 0. Yeah. So the 0 will go to the left first register, right? Yeah. Okay, and the thread? And the thread number 1, where it will point? Yes, on the second instruction. That's right. Yeah. Okay. I press right here, and that's what happens. It went further, and we have 0, 0 in the register. So we have 1 thread now. It points to compare. We can execute compare. And it says compare A or B, and the input character is A. So what happens?
It's very hard to be here also.
Okay, you can stand here maybe. I don't know if it will be easier for you.
Could you ask the question again?
Okay, so what will happen now? We execute this compare instruction, where the thread will point, so where the pointer will be, and will anything else change? Okay, I'll just tell. Yeah, so the thread will point to fork jump, and the input pointer will propagate. Intuitive? Okay. I'll just do it for you. Just track it. So we add fork jump here to L1. What will happen now is the first thread will jump back to L1, and the second thread will go further to save right. And now the numbering of threads that's important because that's how we model the priorities. The threads with lower number will have the higher priority. Okay, so you see there is another register bank here, and it's the clone of the first one. So like when threads fork, they save all the registers. And now we have 1 thread pointing at compare, but not the other. So we we have to unwind this other thread until it points at compare as well. So we do the save write, and you see that second thread in the right register gets 1. That's the pointer to the input stream. And then save left, 1 appears over there. Now we have both at compare. We can execute compare. What will happen? We have this first thread that succeeds on A or B, and we have the second thread that succeeds only on B. So the first thread will survive, and the second one will die, right? That's what happened. Pointer moved over here. No more this thing anymore. Then there is the fork jump again. We do that. Again, compare. Again, save left, save right, save left. Again, this compare. But now it's compare B, and the B is an input stream. So both survive. Both go further. We have this thread number 2 that will get to the end, and the fork jump again. And go next. So we have this thread number 3. It reached the end of the regular expression, but it's a thread with the lowest priority, so we have to continue executing. We'll do that. We propagate thread number 2. It gets to compare. So we have 2 threads at compare, but no input characters, so they both die. Success. And we have two match groups. The first match group is AA, and the second one is just B. What would that be? What regular expression would that be? Can anyone try to guess? So it's A plus B. That's true. Just A plus B. But where the match groups would be? Yeah. So not just A plus, but AB plus. Yeah, like this. Okay. Okay. Thank you, Lucas. Well, you tried. Thanks for trying. All right, and just very quick demonstration of how it will be different, for example, with fork stay, not fork jump. So again, program, we save left, we do the compare works. We do the fork stay, so the first thread went further, and the second thread jumped back, so the thread with the higher priority is going forward. We propagate it, we do the fork stay again, another jump, and now that thread number 2, it finishes executing, and at that point thread number 3 dies. Why that? Because since we say that the thread with the highest priority wins, it means that if thread number 2 already finished executing, it makes no more sense to run thread number 3 because it will never win by the priority. So we do the compare B again, that wins and finishes executing. That is success. And I just show you the regular expression now. Similar one, it's AB plus question mark. You know what that is? Yeah, that's non-greedy. Kleene plus. So there are eager versions of quantifiers and the greedy versions, and the difference is like, yeah, they are either greedy or eager. The greedy ones try to match as much as they can, and the lazy ones, or non-greedy, they will just try not to do any work. Okay. So a few words on the implementation. How can you implement like the common quantifiers, the common regular expressions using these instructions we introduced? So the catenation is very simple. You just catenate the bytecode of different regular expressions one after another. This include thing, it's not an instruction, it's a compiler macro, so to say. And quantifiers, for example, the greedy plus is implemented like we put a label, we just flatten the regular expression inside, and we fork jump onto that label, which means we'll match at least once, and then we'll spin in a loop if we want. And you see the greedy and non-greedy version, they differ, just one uses, in this case, fork jump, the other is fork stay. The Kleene start a little bit more complicated. I won't focus on that very much, but yeah, you can implement all of the quantifiers by using just these instructions. And the alternation as well, one or another. And match groups, you like the syntax would be S, then name of the group, and then the regular expression. That's just save left, the regular expression you want to match, and then save right. Also, I've shown you only examples where the argument to compare was just character, but the whole point was that we want more than that. So arguments to compare could be strings, where you just check string for equality, or any character level regular expression, or some hash set or hash map. Then you will look up the token from the input string in that hash map, let's say, or any arbitrary predicate that you will call, and if it returns true, it means a match. And once all that is done, you can now write regular expressions in this way, if you're not afraid of Lisp and parentheses. So we say as person, it's either the concatenation of optional honorific, then one or more first names, and then the last name, and these things are some predicates or some dictionaries where you can look up the words, or it's optional determiner and the name of the profession. There are a few extra features in our implementation. For example, we support positive and negative look ahead, where you can say I want to match as many names, but unless the next word is the stop word. To implement that, actually we had to give each thread its own sub-virtual machine. So I guess it's too much for today. There are also anchors, start anchors, like the caret sign, the dollar sign. You can put in regular expressions. We have the two. You can get very cheap anchor-free matching. Means you can look for regular expression not just from the beginning of a string or sequence, but anywhere. And it's cheap because you just prepend this non-greedy Kleene star at the beginning of the regular expression, and since the virtual machine guarantees the linearity of runtime, it will stay linear. Whereas with backtracking implementations, what they do, they just try to match the regular expression from every character in this case, and that makes it quadratic. And we also have loop detection. So the example from before, the one that killed the snake, we can run that on any input of any size, and it will finish very, very quickly. My favorite feature of this thing is the composability. So we can, let's say, define some regular expression, like call it numbered street name. So it's one or more alternation of just number or street name. And once we define it, we give it a name. We can use it one or more times in defining other regular expressions. And if you ever did that in Java, you'll know that it's not very convenient in Java, because you'll have to just mash strings together. So you have a regular expression defined, and you concatenate it with the you open and close the parentheses in strings. You create a match group. It's very error prone and not convenient. Here, the regular expressions, they are first-class objects. You can manipulate them however you want. You can compose them conveniently. There are a few shortcomings, of course. There are no look-behinds and no back references. It's the same as Google Re2 implementation, for example. It cannot find all the matches. It only returns the first match defined by the priority of the threads, and it has quite too much complexity for trivial cases. For example, if you want to just find something in the sequence, it's easier just to do the linear scan than to roll this whole machinery. Yeah. And what's exactly under the hood? The first version was written in Clojure. It was just 300 lines of code, very concise, very debuggable. All of the internal objects were immutable, so it was very easy to debug it, because all of the state of the virtual machine was just in one object, and whenever you did a step through, it returned another immutable object. You can save it for future debugging. You can just inspect it and not worry that it will change underneath you. But there was the problem with it. It was slow for our purposes. The real word regular expression on some sentence took around 1 millisecond of runtime, and that was too slow for us. So I took the profiler and tried to see what the main bottlenecks were. And actually, it turned out that the main bottleneck was the repetitive recompilation of regular expressions. So I implemented inline caching of them. To understand what that means, I'll show you this example. What is wrong with this code? Yeah, so this is a loop, right? And in this loop, this regular expression will compile on each iteration, and the compilation it's quite slow compared to the matching, to the subsequent matching. It's slower, so you pay that price over and over again. So what we can do instead, we can compile it once outside of the loop, right? And then just reuse this pattern object. So this is how the cost of this pattern compilation, it is amortized the more times you run the loop. And with the power of Clojure macros, you can do that automatically. So whenever the compiler sees this Trex macro, it will remember the line and the column where it saw it, and then it will cache the compiled regular expression. It will reuse it on subsequent uses. That improved performance 3 times. It was still too slow for the use case. So I started to rewrite the whole thing into Java, part by part. I made some objects mutable, because you might know that immutability has its own overhead. Whenever you could just change some field, you have to create the completely new object. So there is an overhead. So I started making objects mutable. The performance became better. Then I made everything mutable, and the performance became worse, because suddenly, in some cases, I had to do too much copying. For example, in the case of thread forking, when you get 2 threads out of 1, and if the underlying objects are mutable, I had to defensively deep clone them, because I could not rely anymore on them being immutable. I could not just simply share them. So I made some things immutable again, and with that, I arrived the current implementation. It's 300 lines of Java. The virtual machine is completely rewritten to Java with all the internal objects and data structures. And there is still 300 lines of Clojure. The whole compiler is written in Clojure. The quantifiers defined there too, and the public API. And in terms of data structure, it's a mix of mutable and immutable objects. There are copy on write fields. Whenever you change something, actually you get the copy of that. And the performance now, it's 20 times better. So it takes around 50 microseconds to run some arbitrary, some very specific, actually regular expression on some sentence. So it's fuzzy number. The numbers are fuzzy, but that works. So there is some future work I want to do about this. First, to improve the performance of trivial cases. For example, if you take the Rust regexp library, it has this hack. If the regular expression starts with something trivial, for example, some character, it will do the linear scan across the whole string, trying to find that character. It remembers the positions of those characters when it found them, and only then it will start the regular expression machinery inside, and that improves performance quite a bit. So that's what I mean by static analysis on optimizations. We can also employ the JIT compiler on different levels. We can try to compile this custom bytecode into direct Java bytecode, so that we don't interpret the programs written in this funny bytecode, but let Java do it directly, so that it can then use its own JIT compiler to compile it to native code, make it even faster. Another possibility would be to leverage the runtime data of the regular expression. Let's say we have a regular expression that matches an email, and the engine sees that the most common part where it fails is where it doesn't find the add sign. So if we can somehow extract this information from the runtime and then automatically first search for the add sign and only then start the regular expression, that would be cool. I don't know if it's possible, but just fantasies. And we can also add branch prediction, probably. also by knowing where it fails more often, so that finally it's vulnerable to meltdown and we can write to Hacker News about it. And finally, would be really nice to have look behinds, because that's very common NLP demand to have that. So the conclusions. First of all, old papers contain wonderful ideas. This is quite an old paper, and most people don't know about it, but I think the whole technology, the whole idea is very neat, and you can go with this, not just to do regular expressions, but do other things, I guess. And knowledge from university can be useful. I had an assembly course back at college, and at that time we thought it's not very, will not be very helpful in future. But if I didn't take that course, I'll probably will not understand anything here. And the third conclusion is make it work, then make it fast. It's better to do a prototype and just figure out all the implications, so the cornerstones of the task, and then you optimize it to fit the performance demands. So the references, this is the link to the original paper first. The second link is the open source implementation of this idea in Clojure again. So our thing is not open source, but I found this one. This is from where I knew about the paper, and it's very similar to what we did. I took inspiration from it, so I recommend you take a look if you're interested. And the third one, it's not about the regular expressions. It's actually a challenge which was given at some conference a few years ago. And the challenge is you get a binary, just a binary file and a specification of the virtual machine, and you have to implement this virtual machine in any language you want. And then with this virtual machine, you run the binary, and that's where all the fun starts, because this binary is actually a program written in this virtual machine, and it's a kind of like text quest, you know, where you say go east and do stuff, and to finish this quest, you have to debug the memory and, well, all of things. It's very fun. And this is the end of my talk. I also want to say at the Grammarly, we have a booth on this floor. Come to our booth. We have a few interesting programming tasks and regular expression tests over there. So come visit, come say hi. And we also have Java engineer openings, so you can learn more about them at the booth. Thank you.
Do you really need multi-threading for this application? So if all the threads run in lockstep, it sounds like you can use just single thread. No?
When I say multi-threaded, it means that these threads are virtual. So it doesn't exactly map to multiple threads on the operating system level or on the Java level. It's just the abstraction we have. So in case of a simple virtual machine, different threads are just different instruction pointers that you keep track of. So in the end, it's just, yeah, they are only on our level. They're virtual. Those are not real threads. Any more questions? Please.
So any actual numbers on performance comparison between Java native regexes and this implementation?
Okay, so we didn't compare the performance to existing regular expression engines, because the task is a little bit different. I mean, it's probably slower for just if you try to use this to match just ordinary regular expression against strings. This will be slower because I'm sure Java implementation has much better optimizations that we could implement. But as I said at the beginning, the problem was wider than what just ordinary regular expression cover. But we could try to compare it. Probably it will run up slower. Please.
Thanks a lot for a very interesting presentation. So could you reiterate what the actual problem we were trying to solve?
Okay. I'll get... Plenty of slides. So we want to be able to express some rules regarding to natural language in terms that are very familiar, yeah, they look like regular expressions because they are regular expressions in the end. So we want this semantics of optional things and multiple things, 0 or more, 1 or more alternations. So we want to keep the semantics of regular expressions, but we want to do that for the tokens, for the elements of different level, not just characters, but arbitrary objects, let's say, or let's say just strings, full strings. Sorry, yeah, you can take the microphone.
I mean, if I understood the use case correctly, I think this problem can be solved with writing actual parser grammar and using not a regular expression approach, but like write a parser for define a grammar and write a parser for this.
Yeah, that's true. You can go that way. The other problem is that we write a lot of those, and it's very dynamic. So you experiment with it. You just want to you want the feedback loop to be the fastest with this. So we actually wanted something very dynamic, kind of like regular expression, but at the same time as expressive in terms of what you can do.
Okay.
Please.
Yeah, I have a question about the Clojure. Have you tried to make those data structures transient? And have you tried type hinting? I mean, what exactly did make it so much faster in Java?
So first we started with using vectors to represent like some of the internal data structures, and in the end the ones, yeah, whatever. The ones used in Java is just a flat binary array of these instructions and arguments. So there were a lot of things. There were cache misses, and there was overhead for creating these vectors. And even with transients, it's still too much overhead and too much GC pressure when you're using that. So we needed something very very low overhead for the internals of the VM.
Cool, thanks.
Well, that's what worked in the end. Yeah, but the first one was just vectors and stuff.
What does it need to be? You mentioned that it ended up to be 50 microseconds.
Yeah.
What were you looking for? What do you need? Do you need 1 microsecond? Do you need 50 milliseconds? What were you going for? What's an acceptable SLA?
So yeah, the acceptable, because that's like the if you take this thing, it's just a very low level part. So it's an implementation of the regular expressions, but then you write these regular expressions on top of it. So you define some domain level logic for matching different stuff, and we have to run a lot of that, and on many different sentences. So it's kind of like it's heuristics. I mean, if we get 10x more users, maybe we'll have to get back to this, optimize it even more. But it was driven just by how many times this will be called, basically. That's why one millisecond, it seems like not much, but if you have to run it a lot, then you get this just not enough bandwidth to do that.
Cool, thank you.
Thanks. Okay, I think that's it. Thank you. The last question, really liked it. I see that you followed the presentation, so you get a small present from Grammarly. Yeah, and thanks for listening.